Hello everybody and welcome to another episode of Building BlocklyProp. What we're going to do today is we're going to actually build a library in C for the propeller using this little chip, which is a digital potentiometer that's available. It has come with a lot of our kits over the course of the years, and so it's something we have around a lot. But we actually don't have a C library that I'm aware of that goes with this. So what we'll do is we're just starting up with just a plain C library. In fact, what we'll do is we'll do a new project here. So I've got Simple IDE open. We're going to call this, we're going to start with lib, since we intend for this to become a library. Digital, we'll just say libdigitalpot instead of digital potentiometer because it's kind of wordy. We can always go back and change that later, although it's a little bit of a pain to change. And we'll just click Save here. So now we have a blank simple project. And instead of the blank at the top here, I'm going to say library for the AD, you can read the number on here, 5220 digital potentiometer. Hopefully I spelled that correctly. So for startup code, well, let's begin just by going to the data sheet. So what we're going to do is we're going to search for the AD5220 data sheet. I'll just start with Google first, and worst case, if it's not easily available here, oh, there it is. So this is the guy. It's an increment-decrement digital potentiometer, and it's pretty easy to use. Basically, you supply it with voltage and ground, and then you have 3 pins here that effectively act like a potentiometer. What I'm doing in this next section is very quickly, I fast forward it, I'm connecting both the one end of the wiper and the 5-volt line to 5 volts, the ground to the other end of the wipers or the potentiometer, and then connecting the data lines up to the propellers pins 1, 2, and 3. Now, according to the data sheet, let's scroll back at the top, we have 128 positions to choose from. And just a quick read of the data sheet, basically the way this works is we set up or down to be we set up or down to either be high or low, and it looks like our clock line needs to be pulled high, as does our up-down line, now that I'm looking at this. So it looks like we've got a couple of resistors there. So let's just grab a couple of 10K resistors. We've got 1 and 2, just to make sure that this is behaving the way we expect it to. So it looks like our clock line and our up-down line. So these two guys will both need to be pulled high. And since these are directly connected to I/O pins, I'm only going to pull them up to 3.3 volts. I'm not going to pull them up to 5 volts. And we'll hope that our logic levels are sufficient for this to work, but they should be. 3.3 volts is generally high enough for sorts of applications. So those are now pulled up to 3.3 volts. And this up-down, guys, since we're not using a switch, what I'll do is we're digitally controlling that directly with one of the microcontroller pins, so I'm not going to sweat this resistor right now. Okay, so now we are completely connected. And the way this works is we set the up or down pin either high or low, and it looks like chip select is fixed to ground. Now, this is kind of a decision point. Do we want to just say, hey, that should be fixed, or should we drive that with a microcontroller? So if you're running multiple of these potentiometers, you can run all of these data lines parallel, and then you can just use one chip select pin per per device, and that's not necessarily a bad way to go. So let's start that way. And it looks, and the way you basically do this is if you're set to up, then you every time you push the clock line or toggle the clock line, just pulse it up and down, then it increments it one position up to 108 positions, and so it slides the potentiometer across. And that's evident by these oscilloscope screenshots here. I've added an intermission here because if you want to see me stink at coding for the next half hour, by all means continue watching. If you want to see the end result where this thing actually starts to work, you can go ahead and skip to the 35-minute and 43 seconds, somewhere in that vicinity mark, to see this library actually work, and then I'll give you some pointers at where this would go next and how to wrap it all up in order to use it inside of your own Blockly system. So we'll go back to our main code, and the first thing I want to do is we want to essentially guarantee that the chip is going to be set in the 0 position first. So we'll go down. So the first, remember the up, let's actually use some includes so we can keep our pins straight, or some pound defines. So we're going to say that our direction pin, and it looks like we connected up, down. Go back here. We connected up, down to pin 2 and the clock line to pin 1. So we connected that one. Define clock button pin. Sure. 1, and then define digital pot chip select. We put that on pin 3. And these are a little bit ugly, but they're going to tell us what we need to know for now. The first thing we want to do is we want to set the direction pin low. So we will go low, just copy paste, set the direction pin low. I'm going to go back to the data sheet really quickly here. And a number that caught my eye that's important to know is, let's see if I can find this, the interface timing characteristics. You notice that the input clock pulse width, 25 nanoseconds. So that is incredibly short. It basically means that we can just pulse this thing like crazy without delays, and that should do the trick for us. And now we're going to set a loop, and we're just going to pulse this thing down 128 times, and maybe just 130 for good measure. And that way we know we're starting at 0. So we'll say for int, say chip pulse, start at 0. We'll make sure that we're under 128, because 128 pulses ought to do the trick. And chip pulse, we'll just increment it. And each time that happens, we will want to go first. Well, we better actually set that pin low first, just to make sure we get a clean pulse. So we're going to say this is the clock button pin. First, we're going to set the clock button pin high. Then we're going to set it back low, and that will constitute a pulse. And it should just basically loop through this 128 times, and that should bring the chip right to 0. So this first thing happening right here is make sure the 85220 is set to 0. It doesn't start up in some random state. It probably doesn't. It probably starts at 0, but this is just a sort of that added layer of safety. Now what we're going to do is let's actually make a function here. So outside of main, we're going to say that this won't be a function that returns any values, so we'll start with void. Should probably go back and rename these things later. So we'll set digital pot, and we're just going to say this is int wiper, or just I'm struggling to come up with good names for things tonight. Int wiper value. So that'll be the value of the wiper pin. And remember, this can range from 0 to 1, or from, yes, 0 to, it's got 128, so 0 to 127. The best way to guarantee that a number is within 0 to 127 is to just give it some if statements. So we'll say if wiper value is greater than 127, then wiper value equals 127, and if wiper value is less than 0, and same thing, wiper value equals 0. You should be in business there. So now we've sort of made sure that our input is within range, and if somebody throws it something too high or too low, it'll just clamp it to that. And let's let's actually set a variable here that is the current position, and we'll just call this int. We'll precede it with an underscore. Wiper position. We'll say it equals 0 to start. And after we do this business right here, then the wiper position should be at 0 as well. Now our function is going to look just like this too. So we'll copy this guy, and we'll put him inside of our function. And the other thing that I noticed that we didn't do is we didn't do the chip select. So let's actually say that with this digital pot guy right here, let's put the pins in here too. And it's a couple more arguments, but then we can use it somewhat universally. So we'll say this is int CS pin, int CLK pin, int dir pin, and then the value. So you say which 3 pins you want to do this to, and it outputs the value, or sorry, you then give it the value, and then you're pretty much set. So now instead of using these functions, we're going to say direction pin, clock pin, clock pin, clock pin, and realize the wiper position could be any one of these. So let's actually make an array out of this. So we'll say there are 32 possible in the array. The reason I'm doing this is because let's say that you've got a few of these connected to different pins. Then now you know which one. And we'll just designate this to the clock pin. Equals whatever the wiper value that we output. So I'm actually going to delete this because we're going to do this differently now that our program's sort of evolving here. So we've got a function that we've got our pins. So the first part of our function here is to make sure, I'll make sure this is a comment, make sure wiper value is within an appropriate range. Remember, we need to also set the chip select line, or this won't do anything either. We'll do that last just to make sure that these guys are both properly set to CS pin. Pins to starting state. And now how much we want to move it depends on where it was and where we want it to go. So the first thing we want to do is we want to say, what is the wiper value? That's where we intend to go. And where it was is going to be this wiper position for this particular clock pin. Or sorry, not clock pin, CS pin, because the CS pin is the one that will be independent for each chip. So the wiper value minus the wiper position, or at least what we think is the wiper position, is going to tell us both the direction and how many pulses to go. So int, we'll say the distance, and so now we have the travel distance, how far we want it to go. Now we want to ask the question, did it end up being negative? So do we need to go downward? And we actually don't want to set the direction pin here yet, because that's the part we're not sure about. So let's just say that if travel distance is less than 0, so now it's negative, then we want to head downward. So we want to go low, and this is the direction pin. That's the first thing we want to do. We want to set it downward, and then we want to say travel distance equals times -1. The reason for that is because we need it to travel a positive amount of pulses. So that's the first thing we're going to do. And then the else here is that we're going to say the direction pin is high, so that'll make it go upward. So now we've got determine how many pulses and in what direction. And then we set, when we're all done with this, we set the wiper position to whatever the intended wiper value was. So now we have set digital pot, and the only other function we could probably use here is going back to that resetting the digital pot to make sure that it's set to 0. And the way that we're going to do that is we're just going to simply call this function. So we'll say void init digital pot. We'll use the same arguments, CS pin, clock pin, and direction pin. And since we know where we want it to go, we don't need an argument for that. So the first thing we're going to do is we're going to assume that it's at the highest position. So we'll say that the wiper position for this particular guy is all the way up at 127. Then we'll call setDigitalPot and that our desired value is 0. And this will cause it to pulse downward all 128 times. So we'll call, and then we'll say that our desired position is 0. So we're pretending that it's all the way up and that we intend to go for it all the way down. And that should init it just fine. So now we've got our two functions, and it looks like we're pretty much in business. So let's do this. We'll just say we're going to initialize it. And the chip select pin, starting to dislike these guys right here. We'll just say it's the chip select pin is 3. The clock pin is 1, 2. And now, while we're here, let's do pause 1000. We'll wait a second. And now let's just do for int x equals 0. So then 128. X plus equals, should we go by steps of 4 or 8? Is 128 divisible by 8? Hold on, busting out the calculator because I can't do math right now. 128 divided by 8, 16 times. So we'll just say we're going to add 8 each iteration. Oops, I meant to put this inside of the loop. So we'll wait for a second, and then we'll do set digital pot. Same pins, 3, 1, 2, and our desired position is going to be X. And so what this should do is it should loop through, and it should cause the pot to be at a value that's going to be a fractional, and it's going to increment by a set amount. So if we start with 5 volts, and we divide that by 16, then we would expect it to increase by 0.3125, so 3 1/8 volts in each iteration. So let's turn this guy on. Nothing's smoking, so it looks like we're in good shape so far. We'll build this to make sure that it's going to compile correctly. Aha, looks like I made a goof up. Oops, travel distance undeclared. And I'm running an older version of Simple ID and it's freaking out on me, so we're going to just force quit it here. Yes, force quit, I know what it's doing. Come back to Simple IDE. I know. All right, let's look for that travel distance offender here. Oops, bring back my project. Travel distance. Ah, that is because I typed it one way in one place and one way in another. Hopefully that's our only offender. Try this again. Cross our fingers. It compiles correctly this time. No, not quite. What did I screw up this time? Init digital pot, init digital pot. Implicit declaration of function. Oh, I spelled it wrong, of course. All right, one more round we go. So hopefully that's it. I appreciate your patience with me as I fumble through this. Okay, bring back our project again here. And we'll just copy the name to make sure we spelled it correctly. Just for good measure. We'll do this one too. Okay, no whammies, no whammies. Say successful compile, please. All right, cool. We're in business. Okay, so I'm going to fire up the multimeter and measure voltage. And let's see what this thing says initially. And so I apologize, I don't have my meter on the screen just yet. Okay, it's starting at the halfway point just for kicks. So if we run this, let's do this. Let's just move this guy out of the way and put the meter on screen so that you can see what it says. Okay, I'm going to run that, and then I'm going to hold this against. Okay, took it to 0. Cool. So far, so good. Not seeing much happen yet. Oh, that was weird. Yeah, no dice here yet. Doesn't look like we're doing this right yet at all. It's just sitting there. Yeah, it's like she goes up to 5 volts and then back down to 0. So we'll go back to the data sheet and see if I got either directions crossed or wires crossed or something goofy like that. Maybe let's start just for kicks. Start here, see what happens. Maybe I have this all backwards. That was interesting. I kicked it right up to 5 volts right away. Huh. Every 16 seconds, I bet it's reset. So it's probably doing the reset thing, and then it's coming back up. So we're on our way, but it looks like we might be maybe either doing this maybe too fast. So it's possible these pulses are happening a little too quickly. So let's trying to remember what the function here is. I think it's sleep US. Go for a microsecond. I think I better look that function up just to be safe. So let me document, simple IDE, learn, simple libraries, utilities, lib simple tools. just to be sure. So let's go to there is a pause US here. I believe it calls an underlying function. uSleep. There it is. That's the one I was looking for. So uSleep. uSleep. Okay. Another thing, I'm going to go back to the way we had this, and let's run this, and I'm going to go back and check the data sheet and see if I'm reading this correctly. So up, down, correction. So up is positive, down is negative, as the bar over the top means. Control the can be easily generated. Okay. Let's see if that uSleep thing helps. Send this in. All right. So it goes to 0, like we expect. Then it's not moving. It very quickly resets to 5. Let's actually comment this out and see if this int digital pot sends it up to 5 right away. So let's load that. Well, for something that was supposed to be simple, it's kind of turning out to be what a bear here. Yep, 5 volts. So instead of resetting it, it's actually taking it all the way up to 5 volts. So why is it doing that? Let's go back and look through our math here. So our desired position, we're saying it's at 127. So wiper position for the CS pin. We're saying 0 minus 127. That means travel distance will be negative. That means that we are doing... Oh, we never actually did anything with this. Well, that might explain a few things. I want to say it goes travel distance, number of clicks, and we set low to go down if it's less than 0, else high. Okay, cross our fingers. All right, while that's loading, hooking this up. Okay. Yeah, we're starting at 5 again. So I feel something's still backwards. But we're at least on the right track. Let's see if we have the direction wrong. And I'm not so sure we need these uSleep guys. They're just going to slow us down. Not sure that's the problem yet. All right, so we first... Oh, of course, I commented that out. Remember, we're still backwards though. We still not sure why that's not going to 0 initially. So we'll say if travel distance is send 0. Let's try swapping these. Hi. At this point, I'm just kind of trialing erroring it, crossing my fingers, and if I get it right on one of these shots here. Okay, went to 0. And every second it's ticking up just like we want it to. Aha, there we go. 4, 4.5, and back down. Well, there we have it, folks. I think we have a winner. I have to say, that's pretty cool. Okay, so now we have a set of functions that I would think are relatively easy to use. So we have a set and an init. Set digital pot, init digital pot. And just to kind of look really quickly at the naming conventions of things, let's actually just use AD5220 set. And same, we'll use the init. Maybe we should call this reset. That might be a although it kind of big, well, it's actually good because it ensures that it's going to pulse it all the way down to 0 regardless of where it's at, as opposed to going to 0. So the only things we really need to have in our library, we need to have this wiper position, and let's actually go so far as to call this the AD5220 wiper position. Am I using that? I'm using it one more time right there. Let's say less than or equal to 128 because I think we're missing the last one with this plus equals incrementing by 8. Okay, so the wiper, oh, one more of those wiper position things. And the reason to use this AD5220 is that allows us to expand the library to include other digital potentiometers. Like, for instance, there are some SPI variants, both in Analog Device makes some. Yeah, most of the semiconductor manufacturers have a few of these style of chips, and so there are some SPI or I2C ones that we could include within this library as well. This just affords us that ability. The other thing we're going to do is we're going to put static within this, or static int, and what that'll do is it'll restrict this variable to inside of the file. And the last thing we want to do is we have our test harness here, and so now let's add a couple tabs to our project. So we're going to add a tab to project, and we're going to say digital pot as a C, so digitalpot.c. We're going to add another tab to project, digitalpot.h, and this is a, oops, header file. I'm sorry. There we go. Caught my mistake right off the bat. And let's actually grab our functions here. So we're going to X those out. and paste those in the C file. Our two functions and our global variable. Or I should say it's restricted to this page. That's what the static indicates. And now what we'll do is we'll pound include digital pot.h. So far, so good. And inside of the H file, what I'm going to do is I'm actually just going to copy my C file, but what I'm going to do instead is I'm just going to delete all the functions so we just have the declarations themselves. So this is all we need in the H file to make sure those are declared ahead or forward declarations. And then in the C file, we actually have the functions being defined. And now we should be able to go into the linker here, create a project library. We'll build this, make sure nothing errors out on us. And it looks like there were a couple of implicit declaration of low and high. Oh, it's because I forgot to include simple tools in those other files. So let's make sure that's there. So include simple tools. Okay, try that one more time. Even though those are warnings, that would have been catastrophic. It would have made this not work. Okay, the only other thing I'm going to show you is we have the data sheet. We're done with that. So we're going to go to learn.parallax.com. And there's a few more things I'm going to do to this outside of the video. But if I go to search, I'm going to type library in the search bar here. And there's this, scrolling down, how to create a simple library. This is a fantastic tutorial that Andy wrote. So I'm going to follow each of these steps before we do the next video or before we use this in the next video. So when you come back, we'll have a complete library. And I'll show you where it's going to be saved and then how we're going to pull that in and use it in Blockly to create a block to go along with this. So a block for this chip.